As twilight gently fades into the depth of night, a magnificent transformation unfolds above us. The vast dome of the sky, once a brilliant palette of fiery oranges and soft purples, now settles into a canvas of deep indigos and velvety blacks. Upon this perfect backdrop, countless points of light begin to shimmer, each star a distant sun, a beacon whispering stories of cosmic grandeur. Raising our eyes towards the heavens, we find ourselves greeted by an enchanting sight, a soft, milky band stretching across the night sky. This ethereal glow is not merely an artist's stroke on the celestial canvas, but an extraordinary glimpse of the colossal galaxy we call home, the Milky Way. For millennia, humans have looked up at this mysterious river of light, captivated by its beauty and intrigued by its origins. To truly appreciate what we're seeing, it helps to step outside the realm of everyday and consider the night sky as it appears under the darkest, clearest conditions, far from the haze of city lights and air pollution. In such places, the Milky Way reveals itself in astonishing detail. It arcs majestically from horizon to horizon, a shimmering path woven from the combined light of billions of stars, clustered so closely that their individual glimmers blend into a cottony luminosity. Our ancestors, too, were well acquainted with this celestial spectacle. Across cultures and continents, the Milky Way has been a source of myths, legends, and navigation. Some imagined it as a cosmic river, carrying the souls of the departed toward eternal rest. Others saw it as a celestial road, a pathway for gods or heroes traveling the heavens. The name Milky Way itself traces back to the ancient Greeks, who called it Galaxias Kyklos, meaning milky circle. This phrase would eventually transform through Latin into the term familiar to us today. But what is this milky glow exactly? Although it appears to be a continuous band, it is actually composed of an enormous number of stars clustered so densely that our eyes cannot distinguish them individually. Interspersed among these stars, clouds of gas and cosmic dust absorb and scatter light, sculpting the view into intricate patterns of light and shadow. These nebulae give the Milky Way a textured appearance, with dark lanes that thread across its brightness like the cracks of an ancient boulder. To the naked eye, especially from dark rural areas, the Milky Way appears as a pale, diffuse ribbon laden with brighter star clusters and darker voids. These darker regions are not empty, but filled with dense clouds of interstellar material, the raw ingredients from which new stars and planetary systems will eventually emerge. As your gaze follows the band toward the horizon, you might notice that the light thickens and intensifies in one particular direction. This is no coincidence. That glow marks the location of our galaxy's core, a densely packed region filled with stars, dust, and exotic cosmic phenomena. We will come to explore this heart of the Milky Way in much greater depth later, but for now, it remains a distant beacon, hinting at the vast structures hidden beyond what our eyes can perceive. Peering into the Milky Way without assistance has long been a challenge due to its scale and complexity. However, throughout the 20th and 21st centuries, astronomers harnessed new technologies, powerful telescopes, radio waves, and infrared detectors to pierce through the dust and unveil the detailed architecture of our galaxy. This progress transformed our knowing from myth to map, from dream to diagram. When you find yourself beneath a star-studded sky, with the Milky Way flowing gracefully overhead, allow yourself a moment of quiet reflection. Consider that those scattered points of light are suns, many with their own retinues of planets, perhaps even unknown worlds, with conditions far different from our own. The soft glow that blankets the sky is our own cosmic neighborhood, a community of stars bound by gravity, spinning gently within the greater expanse of the universe. As we begin our journey through the Milky Way, it is important to remember that this glowing ribbon is much more than a pretty picture. It is a gateway into understanding our origin, our place, and our future in the cosmos. It invites us on a voyage across space and time, from the closeness of our sun to the distant outskirts of the galactic halo. In the sections to come, we will delve deeper into this celestial city of stars, exploring its shape and structure, the diverse populations of stars that call it home, the mysteries lurking in its dark reaches, and the dynamic forces that sculpt its evolution. But for now, let us remain beneath the quiet majesty of the night sky, embracing the serene moment when our eyes first meet the sprawling river of the Milky Way. As we lift our gaze from the tranquil beauty of the night sky's glowing band, it becomes natural to wonder, what exactly is the Milky Way? To truly grasp this, we must journey beyond poetic imagery and into the realm of cosmic science, where the Milky Way reveals itself not merely as a shimmering stripe of light, but as a vast, dynamic galaxy, a sprawling city of stars, gas, dust, and dark matter, all bound together by gravity and engaged in a grand cosmic dance. At its core, the Milky Way is a barred spiral galaxy, one among countless galaxies scattered throughout the observable universe. When we use the word galaxy, we refer to an enormous assemblage of stars and other matter ranging from millions to trillions in number, intricately held together by mutual gravitational attraction. Our own Milky Way contains somewhere between 100 to 400 billion stars, including our very own Sun, a humble inhabitant of one spiral arm within this colossal structure. To envision the Milky Way more concretely, picture a luminous, rotating pinwheel floating hundreds of thousands of light years across. Its shape is that of a flattened disk, rich with gleaming stars and clouds of interstellar material, punctuated by a dense, spherical core known as the bulge. Surrounding this disk is a large, faint halo composed primarily of ancient stars and globular clusters, tight spheres of stars that orbit far from the main galactic plane. The spiral form of our galaxy is characterized by several sweeping arms, gracefully winding outward from the central bar of stars in the bulge region. These arms are filled with star-forming nebulae and young, bright stars, which give them a strikingly vibrant appearance when observed through telescopes tuned to various wavelengths. Thanks to advancements in observation techniques, astronomers have mapped these spiral arms, uncovering the spatial arrangement of stellar nurseries, star clusters, and molecular clouds within them. But the Milky Way is more than the sum of visible stars and glowing gas. A significant portion of its mass is attributed to dark matter, an elusive, invisible substance we cannot detect directly, but whose presence is inferred through gravitational effects. Dark matter forms an extended halo enveloping the galaxy, crucial to holding the Milky Way together and governing the motions of stars within it. Understanding the Milky Way also means recognizing its immense scale. From our vantage point, roughly 27,000 light-years from the galactic center, in a quiet arm called the Orion Cygnus arm, the galaxy extends about 100,000 to 120,000 light-years across its disk. To put this in perspective, light, the fastest traveler known, takes over 100,000 years just to journey from one edge of the galaxy to the other. Within this vast expanse exist a rich diversity of environments. The dense central bulge hosts an ancient population of stars packed tightly together, including a supermassive black hole named Sagittarius Opus, which anchors the heart of the galaxy. The disk contains younger stars mixed with swirling clouds of gas and dust, where ongoing star formation breathes new life into the galactic ecosystem. High above and below the disk, the halo contains some of the oldest stars and globular clusters, relics of the galaxy's formative epochs. Moreover, the Milky Way is not an isolated island. It forms part of a larger community of galaxies known as the local group, a cluster of about 50 galaxies gravitationally interacting with one another. This neighborhood will become a vital piece of our story as we explore the Milky Way's context in the cosmos. The formation of the Milky Way traces back roughly 13.6 billion years, shortly after the Big Bang. It began as a cloud of primordial gas that coalesced under gravity, forming the first generations of stars and gradually building the complex structure seen today. Over billions of years, processes such as star formation, supernova explosions, and mergers with smaller galaxies have shaped its evolution, leaving behind clues etched in the motions and compositions of stars. Our understanding of the Milky Way continues to grow as modern instruments probe electromagnetic wavelengths beyond visible light. Infrared telescopes can peer through the dust obscuring the galactic center, while radio observatories map cold gas clouds forming future stars. The synergy of these observations paints a richer, more detailed portrait of our galaxy's anatomy and life cycle. The name Milky Way, while poetic, only scratches the surface of this cosmic metropolis's vastness and complexity. It is a galaxy teeming with billions of stars like our Sun, filled with fiery stellar nurseries, enigmatic black holes, and the pervasive shadow of dark matter that shapes its destiny. As our journey through the Milky Way unfolds, we will dive into these myriad facets, exploring its intricate structure, revealing the life cycle of stars, and unraveling the invisible threads that hold this immense system together. But before we venture deeper, it is vital to anchor our understanding in this essential definition. The Milky Way is a barred, spiral galaxy, a magnificent island of stars, gas, and dust that is our cosmic home. It is the grand theater in which the drama of stellar birth and death plays out, a place where we can attempt to decipher the story written in the light of its countless suns. With this foundational perspective, we are now ready to broaden our view even further, to place the Milky Way within the vast web of the universe, and to find our own small but significant place in this cosmic address. From the gentle band of light above us to the tumultuous core far beyond, the Milky Way awaits our exploration. To truly comprehend our place in the vast cosmos, it is essential to understand the grand hierarchy of structures that make up our universe, starting from the galactic scale and expanding outwards into the expansive cosmic web. Our journey begins by pinpointing our home within the Milky Way galaxy, then stepping back progressively to embrace the vastness of the universe and locate our cosmic address. We live on Earth, a small rocky planet circling an average star we call the Sun. The Sun itself is one of hundreds of billions of stars within the Milky Way, a sprawling barred spiral galaxy, approximately 100,000 to 120,000 light-years in diameter. Our solar system is situated roughly 27,000 light-years from the galactic center, residing in a relatively quiet, unassuming region known as the Orion Arm or Orion Spur, a minor spiral arm nestled between two larger arms called the Sagittarius and Perseus arms. This position within the galaxy offers us a unique vantage point for observing the myriad stars, clouds of gas, and other phenomena that compose the Milky Way. The galaxy is not a static entity. It is a dynamic, rotating system where stars, gas, and dark matter move in intricate orbits influenced by the gravitational pull of the collective mass. Our Sun journeys around the galactic center at a staggering velocity of about 828,000 kilometers per hour, completing one orbit approximately every 225 to 250 million years, a time frame known as a galactic year. Expanding our view beyond the Milky Way, we find that it is part of a small assembly of galaxies collectively called the local group. This neighborhood contains more than 50 galaxies, ranging from dwarf galaxies like the Small and Large Magellanic Clouds, visible from the southern hemisphere, to giant spiral galaxies like the Andromeda Galaxy and the Triangulum Galaxy. The local group itself spans about 10 million light-years and is gravitationally bound, meaning the member galaxies are moving around a common point in space. The local group is part of a much larger structure termed the Virgo supercluster, a gargantuan conglomeration of thousands of galaxies, galaxy clusters, and groups spread across roughly 110 million light-years. The Virgo supercluster, in turn, resides within the Laniakea supercluster, an awe-inspiring vast cosmic structure containing about 100,000 galaxies and encompassing a volume over 500 million light-years across. Laniakea's gravitational center lies near the Virgo cluster, exerting a collective influence on the motion of galaxies, including our Milky Way. Looking even further, the universe reveals an intricate cosmic web, an immense network of filaments made up of galaxies and dark matter, intersecting at nodes where galaxy clusters form. Vast voids punctuate this cosmic tapestry, creating a universe with large-scale structure akin to a finely woven cosmic fabric. At the grandest scale, the observable universe extends about 93 billion light-years in diameter, meaning we can receive light that has traveled for billions of years, allowing us to look back in time. Within this unimaginable expanse, countless galaxies swirl and dance, separated by immense cosmic distances. Our Milky Way is just one galaxy among billions, but it is home, the stellar neighborhood where our story unfolds. Despite its small size relative to the universe, the Milky Way's role is profound because it nurtures the conditions necessary for life as we understand it. The precise location of our solar system within a spiral arm offers a hospitable environment, avoiding the intense star formation and radiation near the galactic center and the sparse outskirts where heavy elements required for planet formation are less abundant. Another remarkable perspective comes from considering the speed of light, a universal speed limit that governs how we perceive these cosmic structures. Because light takes time to travel, when we observe distant galaxies, we effectively look back in time, witnessing events as they occurred millions or even billions of years ago. This cosmic time travel enables astronomers to reconstruct the history of galaxy formation and evolution, including the growth and dynamics of our own home, the Milky Way. This brings us to the fundamental concept. Our cosmic address can be summarized as Earth orbiting the Sun, the solar system, within the Orion arm of the Milky Way galaxy. The Milky Way galaxy, part of the local group of galaxies. The local group residing inside the Virgo supercluster. The Virgo supercluster, a member of the Laniakea supercluster, Laniakea, embedded within the cosmic web of the observable universe. Each level of this hierarchy reflects an ever larger scale of cosmic structures, forming a nested set of neighborhoods, just as a house is part of a street, which belongs to a city, within a country, on a continent, atop a planet, orbiting a star. Finding our place within this hierarchy is both humbling and empowering. It emphasizes how, amidst the cosmic vastness and profound ages, we occupy a tiny corner with a unique significance. Our planet harbors life. Our galaxy fostered the elements that allow life's chemistry to flourish, and our position within the cosmic web enables us to look outward and backward in time with growing precision. As we continue to explore the Milky Way itself, from its massive central bulge to the furthest reaches of its halo. We will hold this cosmic address in mind, appreciating the layered scales of the universe and our modest yet extraordinary place within it. This context will enrich our understanding of how the Milky Way connects to the broader cosmos and the forces shaping its destiny. With this cosmic perspective, we stand at the threshold of unveiling the galaxy's intricate structure, its disk, bulge, halo, and beyond, each revealing more about the nature of the Milky Way and our shared cosmic heritage. Imagine the Milky Way as a grand cosmic metropolis, a vast, complex city of stars spread across hundreds of thousands of light-years. To truly understand this magnificent galactic city, we must explore its major districts: the expansive disk, the densely packed bulge, the ethereal halo, and the mysterious realms beyond. Each region contributes uniquely to the galaxy's form, function, and story. At the heart of the Milky Way lies its bulge, a spherical concentration of stars densely packed in the central region. This bulge spans roughly 10,000 light-years across and contains a rich population of old stars, many billions of years aged. Under a telescope, this central hub glows with a warm golden light, a testament to the mature stars residing there. Embedded within the bulge is one of the galaxy's most enigmatic inhabitants, Sagittarius A, a supermassive black hole with a mass of about 4 million suns, quietly anchoring the core region with immense gravity. Surrounding the bulge and stretching outward is the galactic disk, the sprawling, flattened structure that defines the Milky Way's characteristic spiral shape. The disk is immensely broad, measuring about 100,000 light-years in diameter, but surprisingly thin in comparison, roughly 1,000 light-years thick. This disk is the stellar nursery and residential area of the galaxy, home to an estimated 90% of its stars, including our Sun. Within the disk, stars are not simply scattered randomly, but arranged along gracefully curving patterns known as spiral arms. These arms are sites of intense star formation, nestling clusters of hot, young stars, glowing nebulae, and dense molecular clouds, the raw material for birthing new stars. The interstellar medium, a diffuse combination of gas and dust, pervades the disk, weaving connections between stars and shaping their evolution. The disk itself is divided into components: a thin disk and a thick disk. The thin disk hosts most of the ongoing star formation, young and middle-aged stars, and gaseous clouds. The thick disk contains older stars that orbit at a somewhat greater vertical distance from the galactic plane, providing insights into the galaxy's dynamic history and ancient mergers. Beyond the disk and bulge lies the halo, a vast, roughly spherical region extending far above and below the galactic plane, reaching out over 300,000 light-years in radius. Though faint and diffuse, the halo is a crucial component, containing some of the oldest stars in the Milky Way, many packed in dense spherical clusters called globular clusters. These ancient star clusters orbit the galaxy's center in elongated orbits, serving as living relics of the early universe and the Milky Way's formative years. But the halo doesn't contain only stars. It is enveloped by an extensive reservoir of dark matter, an invisible yet dominant presence that exerts gravitational influence to hold the galaxy together and drives its overall rotation. This dark matter halo extends well beyond the reach of visible stars and gas, sculpting the gravitational landscape that governs the orbits of all luminous matter within the galaxy. Additionally, the halo houses a sparse population of hot, ionized gas permeating the space between stars in this region. While the stellar halo stars are ancient and low in heavy elements, this gas is a dynamic participant in galactic ecology, feeding star formation in the disk through a slow rain of infalling matter. In fact, the structure of the Milky Way extends even further. Surrounding the halo is the circumgalactic medium, an enormous envelope of diffuse gas extending hundreds of thousands of light-years from the galaxy's center. This almost ghostly layer is a reservoir for fresh material that can eventually cool and funnel inward, replenishing the galaxy's star-forming regions. It also acts as a protective shield, absorbing and scattering cosmic rays and energetic particles from outside sources. The transitions between these regions are not sharp but gradual, reflecting the continuous interplay of forces shaping the galaxy over billions of years. The orbiting stars and clouds of gas follow complex paths influenced by the combined gravitational pull of visible matter and dark matter alike. One striking feature bridging the bulge and the disk is the galactic bar, a linear structure of stars that stretches across the central region. This bar acts as a dynamical engine, channeling gas inward from the disk towards the nucleus, fueling star formation near the core and shaping the spiral arm's origins. We will explore this fascinating structure in detail later, as it plays a key role in the Milky Way's evolving architecture. To put the scale of all this in perspective, if the Milky Way were a sprawling city, the bulge would be the crowded downtown district, teeming with long-time residents and complex activity. The disk, the vast urban sprawl where most inhabitants live and new life is born. And the halo, the quiet and ancient outskirts filled with historic monuments and old neighborhoods that tell the story of the city's origins and growth. Our solar system lies comfortably within the galactic disk, situated about 27,000 light-years from the center, placing us in a relatively calm and stable environment, away from the intense radiation of the core, but close enough to benefit from the materials enriched through generations of star birth and death. The vastness and complexity of the Milky Way's structure reveal a galaxy alive with history and motion. It is a celestial ecosystem where stars are born, live, and die, where gas flows in cycles that feed future generations of stars, where the invisible hand of dark matter and magnetic fields direct the dance of matter and energy. As we journey onward, the structure we have begun to uncover is the framework upon which the Milky Way's diverse phenomena unfold. Deeper exploration into the spiral arms will uncover stellar nurseries and the ongoing saga of star formation. Looking inward, the galactic bar and central bulge await closer study. And beyond, the vast halo and circumgalactic medium hint at the galaxy's ancient past and future evolution. Thus, standing on the threshold of discovery, we embrace the Milky Way not just as a distant glow across the night, but as an immense and intricate galaxy, a celestial city with distinct neighborhoods, dynamic processes, and a history written in starlight, dust, and the unseen forces that bind it all together. Flowing gracefully outward from the luminous heart of our galaxy lie the Milky Way's spiral arms, the grand architecture where stars and their planetary systems come to life. These magnificent, sweeping structures trace swirling patterns of light and shadow across the galactic disk, a testament to the continuous and dynamic process of stellar birth and evolution. To understand the Milky Way is to appreciate these arms, celestial nurseries where the cosmic cycle of matter, energy, and life unfolds eloquently. The spiral arms can be envisioned as vast curving lanes stretching tens of thousands of light-years in length and composed of billions of stars interwoven with waves of gas and dust. Unlike a fixed set of stars permanently embedded in these arcs, the arms are dynamic density waves, regions of higher density that move through the galactic disk, compressing gas clouds and triggering star formation as material passes through. These arms act as grand cosmic traffic jams, where gas clouds slow down and condense, igniting the birth of bright, young stars that illuminate these regions with brilliant light. There are several major spiral arms identified within the Milky Way that make up its characteristic barred spiral morphology. The principal arms include the Perseus arm, the Scutum Centaurus arm, the Sagittarius arm, and the outer arm. Between these lie smaller spurs and branches, including the Orion spur, our solar system's resident neighborhood within the galactic disk. Among these, the Orion spur is of particular interest because it houses our Sun, a middle-aged star traveling through this relatively quiet arm approximately 27,000 light-years from the galactic center. Although smaller in scale compared to the primary arms, it still contains star-forming regions that provide a peaceful, nurturing environment for the evolution of planetary systems and life. The spiral arms are marked by spectacular clouds of interstellar gas and dust, known as nebulae, some glowing with the luminescent signatures of ionized hydrogen, others darkened by thick dust lanes that obscure the stars behind. These nebulae serve as both the birthplaces and the landscape of young stars. Bright emission nebulae, like the famed Eagle Nebula with its striking pillars of creation, are prime examples where ultraviolet radiation from newborn stars energizes nearby gas, causing it to shine across multiple wavelengths. Embedded within the spiral arms are star clusters, which represent groups of stars born together from the same molecular cloud. Open clusters, such as the Pleiades in the Taurus constellation, sparkle within the arms, their relatively loose associations of hundreds or thousands of stars offering insights into the early stages of stellar evolution. These clusters gradually disperse over millions of years due to the gravitational pull of the galaxy's mass. The formation of stars within the spiral arms is a complex ballet dictated by gravity, turbulence, and magnetic fields. Giant molecular clouds, massive regions of cold gas and dust, serve as stellar nurseries. They collapse under their own gravity, fragmenting into dense cores, protostars gathering mass as their temperatures rise until nuclear fusion ignites, marking the birth of a new star. The star formation rate in the Milky Way's spiral arms is estimated to be about 1 to 2 solar masses of material converted into stars each year. Though this might appear modest on a cosmic scale, it sustains the continual replenishment of the galactic stellar population and enriches the galaxy with heavier elements forged in stellar interiors. Over millions to billions of years, the stars formed in spiral arms will cycle through their life stages, sometimes contributing spectacular endings such as supernovae. These explosions seed the interstellar medium with elements heavier than hydrogen and helium, essential for forming rocky planets and, ultimately, the chemical building blocks of life. Because of the spiral arm's richness in young and massive stars, astronomers frequently study them to understand not only star formation, but also the chemical evolution of the galaxy. Observations across multiple wavelengths, from radio waves that trace cold molecular gas to infrared light that penetrates dust, allow scientists to map the distribution and motions of gas and stars within the arms with increasing precision. Mapping these arms from our vantage point inside the galaxy is challenging. Dust clouds and the vast distances involved obscure direct views, requiring astronomers to rely on indirect methods such as measuring the positions and velocities of star-forming regions, pulsars, and masers, natural cosmic lasers that illuminate the spiral structure. Together, these studies have revealed that the spiral arms are not static patterns, but transient, evolving features. The gravitational interactions within the disk, influenced by the galactic bar and satellite galaxies, modulate the arm's shape and intensity, continuing to sculpt where and how stars are born. Our Sun's passage through the Orion spur brings it periodically closer to denser regions of the galaxy, influencing cosmic ray flux and possibly even Earth's climate over long timescales. This underscores the intimate connection between stellar neighborhoods, in spiral arms, and planetary environments. In embracing the spiral arms, we appreciate the Milky Way's role as a vast, dynamic system, not simply of isolated stars, but of interconnected regions, each contributing to the serene complexity of the galaxy. These arms are the bustling wards of star birth, the gardens of stellar youth amid the cosmic metropolis. As our journey continues, we will descend toward the galaxy's fiery core, where the galactic bar governs the flow of matter and energy, breathing life into the central bulge. We will explore how this central engine shapes the Milky Way's evolution, carrying us deeper into the heart of our cosmic home. Nestled at the very core of the Milky Way lies a fascinating and dynamic structure known as the galactic bar, a vast, elongated concentration of stars that stretches across thousands of light years, serving as the heart and engine room of our galaxy. This stellar bar profoundly influences the shape, motion, and even the future evolution of the Milky Way, acting as a cosmic funnel that shapes the flow of gas, dust, and stars within the inner regions. For many years, the presence of this central bar remained hidden from direct view because the dense clouds of interstellar dust obscure our line of sight toward the galactic center. Only in recent decades, with the advent of infrared astronomy, which can penetrate the thick dust, have astronomers been able to map this bar in detail. Observations reveal that the bar is nearly 27,000 light-years long, about half the diameter of the entire galaxy, making it a dominant feature bridging the central bulge and the surrounding spiral arms. But what exactly is a galactic bar, and why does it matter? Simply put, a galactic bar is an elongated, linear structure composed primarily of old stars, stretching across the central regions of many spiral galaxies, including the Milky Way. Unlike the more familiar spiral arms that wrap around in graceful curves, the bar is a straight, dense arrangement of stars that rotates as a rigid body within the galactic core. The bar's gravitational influence profoundly shapes the kinematics of stars and gas within the galaxy. Acting as a dynamical engine, it channels gas clouds from the outer regions inward toward the galactic center. This inward flow of material nourishes the star formation activity within the central bulge and fuels the activity around Sagittarius A, the supermassive black hole anchoring the galaxy's core. This process of gas funneling is vital for the Milky Way's life cycle. As gas clouds spiral inward along the bar, they can collide and compress, triggering new bursts of star formation in the nuclear regions. This mechanism helps sustain a vibrant, if relatively modest, rate of star birth in the galaxy's heart and nourishes complex cycles of stellar birth and death. Studies suggest that the bar also plays a critical role in redistributing angular momentum throughout the galaxy. By exerting gravitational torques on stars and gas, the bar transfers angular momentum outward, allowing matter to migrate inward more easily. This dynamical dance reshapes the disk and can trigger the formation or modification of spiral arms attached to the bar's ends. Furthermore, the bar is intricately linked to the bulge, blurring the lines between these central components. The boxy or peanut-shaped bulge seen in our galaxy's center likely owes its distinctive shape to the three-dimensional structure of the bar itself, twisted and buckled by gravitational instabilities over billions of years. The origin of the galactic bar is intertwined with the Milky Way's evolutionary history. It is believed that bars can form spontaneously from instabilities in the rotating disk of stars. Over cosmic time, these instabilities grow, elongate, and settle into the stable bar formation we observe today. Simulations have shown that bars can have profound effects on the morphology and evolution of their host galaxies, often strengthening spiral arm features and enhancing central star formation. Bars are not unique to the Milky Way. Roughly 2/3 of all spiral galaxies exhibit bars, making them some of the most common large-scale structures in the universe. This prevalence points to their importance in galactic dynamics and evolution. However, each galactic bar is unique, differing in size, strength, and pattern speed, reflecting the individual history and conditions of its host galaxy. In addition to stars and gas, the bar region is also a complex environment for dust and magnetic fields. Interstellar dust lanes are often observed along the leading edges of galactic bars, tracing shocks formed when gas flows encounter the bar's gravitational potential. Magnetic fields can become compressed and align along these lanes, influencing gas dynamics and star formation. From our vantage point on Earth, located about 27,000 light-years from this bustling core, we appreciate the galactic bar as an essential and vibrant heart of our galaxy. It not only shapes the physical structure of the Milky Way, but also orchestrates the flow of matter and energy that defines the processes taking place in the heart of the galaxy. Moving forward in our exploration, the galactic bar invites us to delve ever deeper into the fiery hub of the Milky Way, the central bulge and its surroundings, where extreme environments, ancient star populations, and the enigmatic supermassive black hole coexist in a delicate cosmic balance. This heart of the galaxy pulses not only with light, but with the dynamic forces that have shaped the Milky Way's past and continue to influence its future. Mapping the Milky Way is akin to trying to chart a vast, sprawling city while standing deep within one of its neighborhoods, the view obscured by buildings, fog, and countless bustling streets. Our position inside the galactic disk presents astronomers with a unique but challenging vantage point. We are surrounded on all sides by the very stars and clouds we seek to measure, and much of the galaxy's structure is hidden behind thick curtains of interstellar dust. For centuries, this impeded our efforts to understand the true layout of our home galaxy. Yet, thanks to advances in telescope technology and observational methods, modern astronomy has unveiled much of the Milky Way's grand design, chasing stars across multiple wavelengths to piece together an intricate map. At the dawn of astronomy, the Milky Way was simply a band of milky light arcing across the sky, recorded in myths and sketches, but not understood scientifically. Early attempts to gauge its size and shape were speculative. In the early 20th century, astronomers like Harlow Shapley used observations of globular clusters to deduce that the Sun lies far from the galactic center, overturning earlier beliefs that placed Earth at the heart of the cosmos. A crucial breakthrough came with the development of radio astronomy in the mid-20th century. Radio waves can penetrate the dense clouds of dust that block visible light, unlocking views of the cold hydrogen gas distributed across the galactic disk. The 21-centimeter line emission, produced by neutral hydrogen atoms changing their energy states, became a fundamental tool for plotting the spiral structure and rotation of the Milky Way. Observations of Doppler shifts in this radio emission allowed astronomers to infer the velocity and distance of gas clouds, revealing the positions of spiral arms and the rotation curve of the galaxy. Infrared astronomy further revolutionized our view. Infrared light also pierces through dust, reaching us from the dense stellar populations near the galactic center and within obscured star-forming regions. Spaceborne telescopes such as the Spitzer Space Telescope and the Wide-Field Infrared Survey Explorer, WISE, have provided detailed maps of stars and interstellar clouds, unveiling the bar structure and spiral arms with unprecedented clarity. Modern optical surveys, pushed to greater depths and precision by instruments like the European Space Agency's Gaia Observatory, extend our stellar census by mapping the positions and motions of over 1 billion stars, with exquisite accuracy. Gaia's astrometric data allow us to decode the three-dimensional structure of the Milky Way, tracing streams of stars left by past mergers and untangling the motions within the disk and halo. This ambitious stellar census is a cornerstone for constructing a living map that evolves with new data. Additionally, techniques involving other types of objects help piece together the galactic mosaic. Pulsars, rapidly spinning neutron stars emitting beams of radiation, serve as precise cosmic lighthouses. Their distribution offers clues about galactic structure, while masers, naturally occurring astrophysical lasers emitted from star-forming regions, act as millimeter and radio wave beacons that pinpoint locations and motions within spiral arms. Complementing these observational tools are sophisticated computer simulations rooted in gravitational physics and hydrodynamics. These simulations help fill gaps in direct observation, allowing astronomers to test hypotheses about the galaxy's past and predict future evolution by modeling interactions between stars, gas, and dark matter over billions of years. The combination of multi-wavelength observations and theoretical modeling has culminated in a dramatically clearer picture. We now recognize the Milky Way as a barred spiral galaxy with multiple major spiral arms and numerous smaller substructures, a central bar stretching across the inner regions, a compact bulge housing an ancient stellar population and a supermassive black hole, and a vast halo of stars and dark matter enveloping the system. However, challenges remain. Mapping the far edges of the Milky Way, deciphering the detailed physics of spiral arm formation, and understanding the intricate interplay between the bar and the disk still push the boundaries of our methods and instruments. Efforts like the Large Synoptic Survey Telescope, now the Vera C. Rubin Observatory, the Square Kilometer Array, and upcoming space missions promise to take stellar cartography to even greater heights. Our pursuit of the Milky Way's structure is not purely academic. It fuels our deeper connection with the cosmos, helps calibrate our models of galaxy formation and evolution, and provides a context for locating our solar system's journey through the galaxy. As we track stars, chart gas clouds, and listen to the faint signals crossing the galaxy, we craft a living tapestry, a dynamic map that tells the intricate story of our galactic home. In this unfolding voyage of discovery, the challenges of our interior vantage point inspire ever more creative and sensitive telescopes. From ancient naked-eye observations to cutting-edge space observatories, the quest to map our galaxy continues, a cosmic treasure hunt through star fields, nebulae, and mysterious dark matter, charting a galaxy teeming with life and motion. As we step deeper into the intricate fabric of the Milky Way, the stars themselves emerge as the fundamental storytellers of our galaxy's history and evolution. These luminous bodies come in a vast array of ages, compositions, and characteristics, collectively known as stellar populations. By examining these stellar populations, ranging from bright, newly born stars to ancient, weathered relics, we uncover the layered narrative of the Milky Way's past, the processes shaping its present, and clues about its future. Astronomers classify stars broadly into three main populations, originally defined in the mid-20th century, based upon their age, chemical composition, and location within the galaxy. These categories, population 1, 2, and 3, though refined over time, provide a conceptual framework for understanding the diversity of stars in the Milky Way. Population IBI stars, often called young stars, are rich in what astronomers term metals. In astrophysics, metals mean any element heavier than hydrogen and helium. These stars harbor significant amounts of elements such as carbon, oxygen, iron, and nitrogen, forged in previous generations of stars. The presence of these metals carries profound implications. It means population 1 stars are part of a mature generation, formed from gas enriched by stellar processes. They tend to be found predominantly in the galactic disk, especially within the spiral arms where ongoing star formation creates clusters of young, luminous stars, commonly blue or white in color. Our Sun is classified as a population 1 star, a middle-aged star approximately 4.6 billion years old, representative of this chemically richer cohort. These stars tend to have relatively orderly, circular orbits around the galactic center, moving within the thin disk plane where gas and dust congregate. In contrast, population 2 stars are older and metal-poor. These stars are typically found in the galactic bulge and halo, regions that formed earlier in the Milky Way's history. The scarcity of heavier elements indicates they originated from primordial gas clouds that had experienced fewer cycles of star birth and death. Population 2 stars are often redder, cooler, and exhibit more elliptical and inclined orbits, sometimes plunging through the disk as they orbit the galaxy. Globular clusters, dense and spherical assemblages of ancient stars found in the halo, consist nearly exclusively of population 2 stars, with ages reaching upwards of 10 to 13 billion years. These clusters provide a living fossil record, holding clues to the conditions in the early universe. Then there is the hypothetical population 3 stars, theorized as the universe's very first stars, formed just after the Big Bang from pristine hydrogen and helium with virtually no metals. These stars are believed to have been massive, short-lived, and now long extinct, as none have yet been observed directly. Their temporary existence set the stage for metal enrichment of the interstellar medium, enabling subsequent generations of stars to form with heavier elements. Within these populations, there is further diversity shaped by a star's mass and life cycle phase. Massive, young stars burn hot and bright, often living only a few million years before ending in supernovae that disperse heavy elements back into the galaxy. Smaller stars like the Sun emit steadier light over billions of years, serving as stable engines for potential planetary systems. Age and chemistry combined yield insightful diagnostic tools. By measuring a star's metal content, astronomers infer its generation and thus piece together a timeline of galactic formation events. Stars closer to the center of the Milky Way generally contain higher metallicity due to continuous star formation and recycling of materials, while stars in the halo tend to be older and more metal-poor. Beyond the Milky Way's internal narrative, studying stellar populations informs our understanding of galactic interactions and mergers. Streams of stars moving together through the halo, often enriched with population 2 stars, attest to past collisions with smaller galaxies that the Milky Way has absorbed over billions of years. These stellar streams act like cosmic breadcrumbs, marking the galaxy's cannibalistic growth. Our own solar neighborhood is but a small sample of this vast diversity. Surveys from missions such as Gaia have cataloged stellar properties and motions for over 1 billion stars, vastly expanding our ability to untangle the galaxy's dynamic history through its stellar tapestry. In essence, the Milky Way is far from a uniform collection of stars. It is a layered, living archive spanning cosmic time. Young populational site stars shine vigorously in the galactic disk's spiral arms, illuminating active regions of star formation and galactic renewal. Middle-aged stars like our Sun embody a balanced chemical composition and stable orbital patterns. Ancient population 2 stars, dwelling in the bulge and halo, carry the secrets of our galaxy's chaotic youth and earliest formative epochs. By studying these stellar populations, we gain a nuanced understanding of how our galaxy grew from primordial gas into the majestic barred spiral we call home. This vibrant mosaic of stars not only lights up the night sky, but also encodes the history of cosmic processes, producing the elements essential for planets, life, and the ongoing story of the universe itself. As we continue our journey through the Milky Way, this understanding of stellar populations will illuminate the processes behind star formation in nebulae, the clustering of stars, and the dramatic end stages of stellar evolution. Each a vital chapter in the galaxy's unfolding story. Within the vast tapestry of the Milky Way, the birth of stars unfolds in some of the most mesmerizing and gentle regions of the cosmos. Nebulae and stellar nurseries, where clouds of gas and dust gather, collapse, and kindle new fires. As we peer into these serene and tumultuous cradles of creation, we unveil the complex and wondrous processes through which the galaxy continually renews itself, casting light into the darkness and forging the elements essential for planets and, ultimately, life. Star formation begins in giant molecular clouds, massive cold conglomerations primarily composed of hydrogen molecules with traces of helium and tiny quantities of heavier elements. These complexes, often spanning tens to hundreds of light years, are the coldest and densest regions of the interstellar medium. Their temperatures dip to just a few tens of degrees above absolute zero, providing a calm and stable environment where gravity can gradually take hold. Within these molecular clouds, pockets of higher density emerge due to turbulence, collisions, or the influence of nearby events such as shock waves from supernovae or the pressure of stellar winds from massive stars. These denser regions begin to collapse under their own gravity, slowly concentrating material. As collapse proceeds, the cloud fragments into smaller clumps or cores, each destined to become one or more stars. One of the iconic visual representations of star formation is found in emission nebulae, glowing clouds lit by the energetic radiation of newly formed stars embedded within. Ultraviolet radiation ionizes surrounding hydrogen atoms, causing the gas to emit the characteristic red glow of H-alpha emission, a vivid and ethereal light that has fascinated observers for centuries. Famous examples include the Orion Nebula, visible to the naked eye in the constellation Orion, and the Eagle Nebula, whose pillars of creation showcase dense pillars of gas sculpted by intense stellar winds. As the collapsing core contracts, it heats up and begins to spin, forming what astronomers call a protostar at the center. This early stage is marked by vigorous accretion from the surrounding envelope of material, with the protostar feeding on the gas and dust in its immediate vicinity. Protostellar disks often form around these protostars, rotating reservoirs of dust and gas that can eventually coalesce into planets, moons, and other bodies, a cosmic prelude to the formation of planetary systems like our own. Protostars do not yet shine from nuclear fusion. Instead, their luminosity primarily arises from the release of gravitational potential energy as they contract. Over hundreds of thousands to a few million years, as pressure and temperature in the core rise, the protostar evolves, shedding obscuring material and clearing its surroundings. When the core temperature reaches approximately 10 million Kelvin, hydrogen fusion ignites, marking the birth of a new star on the main sequence, the stage where it will spend the majority of its life stably fusing hydrogen into helium and producing energy. The young star may continue to influence its surroundings through intense radiation and stellar winds, often carving out cavities or triggering further star formation in neighboring regions. Stellar nurseries, or clusters of recently formed stars, typically emerge within these molecular clouds. Open clusters, loose assemblies of a few hundred to a few thousand stars, illuminate the surrounding gas with their combined energies, gradually dispersing the natal gas over time due to radiation pressure and winds. Over tens to hundreds of millions of years, the stars drift apart, becoming part of the galactic disk's stellar population. An additional important aspect of star formation is the complex chemistry within nebulae and protostellar disks. The interactions and reactions of molecules and dust grains set the stage for the eventual formation of complex organic compounds, the initial steps toward prebiotic chemistry. Understanding these processes sheds light on the origin of life's building blocks and the conditions that foster habitable environments. Feedback mechanisms regulate star formation rates within the galaxy. While gravity acts to collapse clouds and birth stars, energetic processes from massive young stars, including radiation, stellar winds, and supernova explosions, inject energy back into the interstellar medium, disrupting clouds, halting or triggering new star formation nearby, and shaping the galactic ecosystem. This interplay maintains a delicate balance, preventing runaway star formation or stagnation. The rate at which the Milky Way forms new stars is modest by cosmic standards, estimated at about 1 to 2 solar masses per year, a figure that sustains the galactic population and replenishes the cycle of cosmic matter. Modern technological advances allow astronomers to peer inside these stellar nurseries with increasing detail. Infrared telescopes, space-based observatories, and radio instruments pierce through the obscuring dust to reveal protostars, accretion disks, and jets, narrow streams of matter ejected along the poles of evolving stars. Observations uncover the great diversity in star formation environments, from sparsely populated regions forming low-mass stars to dense clusters spawning massive, luminous stars that profoundly influence their region. Beyond the Milky Way, star formation follows similar principles but often varies under different galactic conditions. By comparing star-forming regions across various galaxies, scientists deepen their understanding of how environment and cosmic history shape stellar births. Thus, the process of star formation is a beautiful synthesis of physics and chemistry, orchestrated by gravity and influenced by feedback and environment. It binds the Milky Way's past and future, connects vast clouds of gas to the light of newborn stars, and ultimately creates the environments where planets and life itself may arise. As we continue our voyage through the Milky Way, the next chapters will lead us to the star clusters arising from these processes, open clusters radiating youth and globular clusters whispering ancient tales, each representing a unique stage in the life journey of stars within our galactic home. Nestled within the grand expanses of the Milky Way lie some of its most captivating and instructive inhabitants: star clusters. These dazzling congregations of stars offer profound insights into stellar evolution, galactic dynamics, and the cosmic history of our galaxy. Among these clusters, two distinct types stand prominently: open clusters and globular clusters. Each uniquely embodies a chapter in the galaxy's life and provides a glimpse into the grandeur and complexity of the Milky Way's stellar populations. Open clusters are the youthful neighborhoods of the galaxy, vibrant groups of stars loosely bound by gravity that emerge from the same molecular cloud. They typically contain anywhere from a few dozen to several thousand stars and are found predominantly within the galaxy's disk, especially along the spiral arms where star formation is active. The Pleiades in the constellation Taurus and the Hyades nearby are iconic examples, visible even to the naked eye on clear nights. Formed relatively recently on cosmic timescales, often less than a few 100 million years ago, open clusters are rich in young, hot, blue-white stars radiating brightly. Because their members originated from the same gas cloud, At roughly the same time and are at similar distances, open clusters serve as natural laboratories for astronomers to study how stars age, evolve, and disperse. Over time, open clusters gradually lose their members as gravitational interactions with nearby stars, molecular clouds, and the tidal forces of the Milky Way tug at the stars, causing the cluster to dissipate into the general galactic population. In a few 100 million to a billion years, an open cluster can dissolve entirely, its stars drifting individually into the wider galactic disk. This transient existence highlights how open clusters represent snapshots of stellar families in their youth. In contrast, globular clusters are the ancient, stately cities of the Milky Way's halo and bulge, tightly bound spherical collections of tens of thousands to millions of stars. These clusters date back nearly to the dawn of the galaxy, with ages exceeding 10 billion years, making them some of the oldest known stellar systems in the universe. Their stars are predominantly old, metal-poor, and redder in color, reflecting their primordial origins. Globular clusters are densely packed, with stars huddled close enough to experience complex gravitational interactions. At their centers, the stellar density can be hundreds or thousands of times greater than that in the solar neighborhood, creating environments where dynamic encounters, binary star formation, and even exotic phenomena like millisecond pulsars or low-mass X-ray binaries arise. Unlike open clusters, globular clusters are remarkably stable and long-lived structures. Their deep gravitational wells help preserve them against the disruptive forces of the galactic environment, allowing them to orbit the Milky Way's center as coherent stellar swarms in the halo and bulge regions. Many globular clusters are moving on elliptical or inclined orbits, bearing witness to the galaxy's turbulent formation history and accretion of smaller systems. Studying globular clusters not only illuminates the early epochs of star formation, but also refines our understanding of stellar dynamics under extreme density. They serve as cosmic chronometers, helping calibrate the age of the Milky Way and, by extension, the universe itself. Intriguingly, some globular clusters may be the remnants of dwarf galaxies cannibalized by the Milky Way, fallen satellites whose cores survive as compact clusters. This discovery links the population of globular clusters to the Milky Way's growth through mergers, highlighting their essential role in galactic archaeology. Within both types of clusters, astronomers observe a wide spectrum of stellar life stages. From hot, massive stars burning quickly in youthful open clusters to red giants and faint white dwarfs populating ancient globular clusters. These assortments enable researchers to delineate stellar evolutionary tracks and quantify chemical abundances with unparalleled precision. Modern surveys employing space telescopes like Hubble and Gaia have vastly expanded our catalog of clusters, mapping their positions, motions, and stellar content with exquisite detail. These observations reveal that clusters are not static relics, but dynamic systems evolving over cosmic time, influencing and being influenced by the galactic environment. Open and globular star clusters together form a rich tapestry within the Milky Way, linking youthful stellar neighborhoods with the galaxy's primordial past. As we continue our exploration, understanding these clusters sets the stage for delving into the broader spectrum of stellar lives, from the steady middle age of main-sequence stars to the spectacular ends of giants and supernovae, unfolding the magnificent drama playing out across our galactic home. Stars are the fundamental building blocks of galaxies, and their lives span vast epochs, billions to trillions of years, marked by phases of calm stability and explosive transformations. In the Milky Way, the drama of stellar life unfolds on a grand stage, tracing pathways from youthful main-sequence stars to giant luminous behemoths, and sometimes catastrophic supernovae, which enrich the cosmic environment with elements vital for planets and life. At the heart of most stars' existence lies the main sequence phase, the longest and most stable period in a star's life, during which it steadily fuses hydrogen atoms into helium deep within its core. This fusion process releases tremendous energy, generating outward pressure that balances the gravitational forces trying to collapse the star. The duration of this phase depends largely on the star's initial mass, a delicate balance between fuel and gravitational pull. Our own Sun, a G-type main sequence star, is currently in this stable phase, having burned hydrogen for about 4.6 billion years and expected to continue for roughly another 5 billion years. Main sequence stars vary widely in size and brightness. Massive, hot, blue O-type stars burn their fuel rapidly in mere millions of years, shining intensely but dying young, while smaller, cooler M-type red dwarfs conserve fuel and can persist for tens to hundreds of billions of years. As stars exhaust the hydrogen in their cores, they transition into a more dramatic evolutionary stage, becoming red giants or supergiants depending on their mass. Without hydrogen fusion to support their cores, these stars contract gravitationally, causing their outer layers to expand and cool, resulting in great increases in size and luminosity. These giants can be hundreds to thousands of times larger than their original main sequence size, their cool, reddish surfaces glowing faintly, but their total energy output soaring. Within this phase, for stars of certain mass ranges, the fusion of heavier elements begins in successive shells around the core. Helium fuses into carbon and oxygen, and in the most massive stars, fusion continues up to iron. However, iron cannot release energy through fusion, marking a critical turning point. When massive stars, those with masses typically above 8 times that of the Sun, reach the stage of iron core formation, they face an inevitable collapse. Their cores implode under gravity within seconds, leading to a stunning supernova explosion. This cataclysmic event releases more energy in a brief span than our Sun will emit over its entire lifetime, dispersing elements forged in both the star's life and explosion into space. These heavy elements, including those essential for technology and life, seed the interstellar medium, becoming part of future stars, planets, and ultimately the chemistry of life itself. Supernovae also leave behind exotic remnants. Depending on the original star's mass, the core may become an incredibly dense neutron star, an object of unfathomable density composed primarily of neutrons, or collapse further into a black hole with gravity so strong that not even light can escape. Lower mass stars, like our Sun, end their lives less dramatically. After the red giant phase, they shed their outer layers in gentle winds, creating beautiful planetary nebulae, glowing shells of ionized gas illuminated by the remaining hot core. This core remnant contracts into a white dwarf, a dense, Earth-sized stellar cinder slowly cooling over billions of years. Throughout their lives, stars also influence their surroundings through stellar winds and radiation, shaping the interstellar medium and triggering subsequent generations of star formation. Massive stars, in particular, with their short but furious lives, dramatically sculpt the cosmic environment around them. Modern astronomy unites observation and theory to decipher these stellar life cycles. High-resolution telescopes capture the vivid colors and structures of star-forming regions, giant stars, and supernova remnants, while spectral analysis reveals their chemical makeup and physical properties. By studying populations of stars at different stages, astronomers reconstruct the history and evolution not only of individual stars, but of the Milky Way itself. Thus, the life of a star is a symphony of physics and chemistry, a delicate balance of fusion and gravity playing out over cosmic timescales. From the steady hum of main sequence fusion to the spectacular deaths of supernovae, stars weave the elemental fabric of the galaxy and illuminate the path from gas clouds to planets and potentially life. As our exploration continues, we shall encounter the myriad exotic stellar remnants, white dwarfs, neutron stars, and black holes that stand as silent witnesses to the transformative power of stellar evolution within our magnificent Milky Way. Within the vast and varied family of stars in the Milky Way, some end their lives by transforming into exotic and enigmatic objects that challenge our understanding of physics and the nature of matter itself. These remnants, white dwarfs, neutron stars, and black holes, are not just cosmic curiosities, but essential actors in the evolutionary story of the galaxy, each embodying extreme states of matter and gravitational phenomena that capture the imagination. Let us begin with white dwarfs, the remnants of stars with masses similar to or up to about 8 times that of our Sun. After spending billions of years quietly fusing hydrogen into helium and then evolving through later stages, these stars shed their outer layers, creating beautiful planetary nebulae, and leave behind dense, compact cores known as white dwarfs. Imagine compressing a mass comparable to the Sun's into a volume about the size of Earth. White dwarfs are incredibly dense, with matter packed so tightly that a teaspoonful would weigh tons. Their composition is typically carbon and oxygen nuclei immersed in a sea of degenerate electrons, a state of matter that resists further compression through quantum mechanical effects known as electron degeneracy pressure. White dwarfs no longer perform nuclear fusion. Instead, they slowly radiate away their residual heat over billions of years, cooling progressively to become faint, eventually fading into black dwarfs, cooled remnants theorized but not yet observed due to the universe's age. Some white dwarfs, especially those in binary star systems, can accumulate matter from their companions, leading to fascinating phenomena such as novae, thermonuclear explosions on the white dwarf's surface, or, in critical cases, triggering a catastrophic supernova. Neutron stars arise from the deaths of more massive stars, typically those with initial masses between about 8 and 20 to 30 times that of the Sun. When such a star exhausts its nuclear fuel, its iron core collapses under gravity, compressing protons and electrons together into neutrons, a process that creates an ultra-dense neutron core only about 20 kilometers in diameter, but containing more mass than the Sun. This collapse releases a tremendous amount of energy in a supernova explosion, scattering the star's outer layers and enriching the interstellar medium with heavy elements. Neutron stars are extraordinary in their density and magnetic properties. A single cubic centimeter of neutron star material can weigh nearly 1 billion tons. They often spin rapidly, with some rotating hundreds of times per second, emitting beams of electromagnetic radiation detectable as pulsars if Earth lies in the path of their lighthouse-like beams. Neutron stars also exhibit immense magnetic fields, trillions of times stronger than Earth's, making them some of the universe's most magnetic objects. In some binary systems, neutron stars can accumulate matter from companions, leading to X-ray emission and complex interactions that provide windows into RHE physics of matter under extreme conditions. Finally, at the most extreme end of the stellar remnant scale lie black holes. Formed from the gravitational collapse of the cores of the most massive stars, typically over 20 solar masses, or through subsequent mergers and accretion, black holes are regions where gravity is so intense that not even light can escape their grasp. The boundary beyond which escape is impossible is called the event horizon. Black holes in the Milky Way vary from stellar mass black holes, remnants of individual massive stars, to the supermassive black hole Sagittarius A, residing at the galactic center with a mass 4 million times that of the Sun. While black holes emit no light, their presence is inferred from their gravitational influence on nearby stars and gas, as well as from high-energy radiation produced by matter spiraling into them in accretion disks. These exotic objects, white dwarfs, neutron stars, and black holes, play crucial roles in galactic ecology. Their formation recycles material, triggers high-energy phenomena, and shapes the interstellar environment. They are natural laboratories for testing fundamental physics, from quantum mechanics to general relativity. Understanding these remnants enriches our comprehension of the life cycles of stars and the transformative forces at play in the Milky Way, deepening our appreciation for the intricate and powerful cosmic processes occurring in our galactic home. At the very heart of the Milky Way resides one of the most enigmatic and powerful objects in our galaxy, Sagittarius A, a supermassive black hole with a mass approximately 4 million times that of our Sun. This gravitational titan anchors the galaxy's core, quietly shaping the orbits of stars, gas, and dust within its immediate neighborhood, and offering profound opportunities to study the extraordinary physics of black holes and their influence on galactic evolution. Sagittarius A4 lies about 26,000 light-years from Earth in the direction of the constellation Sagittarius, obscured from direct optical view by dense clouds of interstellar dust and gas. Its discovery came through observations at radio wavelengths, where astronomers detected a compact, bright radio source at the galactic center. Subsequent infrared and X-ray observations allowed scientists to track stars orbiting this invisible focal point, revealing motions that implied a tremendously massive yet extremely compact object lurking unseen. The evidence is compelling. No known cluster of stars or other visible mass could produce the observed gravitational effects, leaving a supermassive black hole as the only plausible explanation. Stars like S2 orbit Sagittarius A with astonishing speed and precision, completing orbits within mere decades and tracing paths dictated by the black hole's intense gravitational pull. These measurements, made possible through decades of high-precision observations, provided the best direct proof yet of black holes existing as real astrophysical objects. Supermassive black holes like Sagittarius A occupy the centers of most large galaxies, hinting at an intimate connection with galaxy formation and growth. Their masses, which range from millions to billions of times that of the Sun, exert influence far beyond their horizons, affecting star formation rates, gas dynamics, and overall galactic structure. Sagittarius A is relatively quiet compared to active black holes found in other galaxies, which unleash tremendous energy through accretion of matter. Our black hole inlet remains in a low activity state, occasionally emitting flares visible in X-ray and infrared light, possibly triggered by accretion of gas clouds or small objects wandering too close. This subdued nature allows astronomers to study its properties without the overwhelming brightness that characterizes more active galactic nuclei. Around Sagittarius AI lies the nuclear star cluster, a dense assembly of stars with varying ages, including massive young stars formed within the last few million years. The environment is harsh, with intense radiation, tidal forces, and complex interactions sculpting the region's intriguing dynamics and star formation history. Understanding these processes sheds light on how supermassive black holes and their host galaxies co-evolve. Studying Sagittarius A offers a unique natural laboratory to test theories of gravity and general relativity under extreme conditions. The recent detection of gravitational waves from merging black holes by observatories like LIGO has revolutionized our understanding, yet direct imaging and precise measurements around Sagittarius A's quakes remain essential to probing the nature of spacetime near event horizons. An iconic milestone was achieved in 2019 when the Event Horizon Telescope collaboration unveiled the first-ever image of a black hole's event horizon, the glowing shadow against a swirling ring of matter, though that was of a supermassive black hole in a distant galaxy. Sagittarius A remains a prime target for similar imaging efforts, with the promise of revealing details about the immediate surroundings of our own supermassive neighbor. In the grand tapestry of the Milky Way, Sagittarius A Phi serves as an unseen yet mighty anchor, quietly mastering the orbits of countless stars and acting as a central participant in our galaxy's ongoing story. Its study continues to captivate astronomers and physicists alike, offering glimpses into the fundamental workings of the cosmos and the profound mysteries that remain at the intersection of gravity, matter, and space. As we move onward in our journey, deeper exploration of the interstellar medium that permeates the space between stars will reveal further complexities and interactions surrounding this supermassive black hole, enriching our understanding of the Milky Way's vibrant and dynamic heart. Between the glittering constellations and shimmering stars lies a vast, tenuous expanse known as the interstellar medium, or simply the ISM, the mixture of gas, dust, and energetic particles that fills the space between stellar systems in the Milky Way. Though incredibly diffuse compared to Earth's atmosphere, the ISM plays a vital role in the life cycle of stars and the overall evolution of our galaxy, serving both as a cradle for new stars and a repository for the remnants of old ones. The interstellar medium is composed primarily of hydrogen, the most abundant element in the universe, existing mostly in atomic or molecular form. Alongside hydrogen, helium accounts for the next largest fraction, with trace amounts of heavier elements and dust grains. These dust particles, tiny solid fragments composed of elements like carbon, silicon, oxygen, and iron, are typically less than a micrometer in size, but collectively have a sizable influence on the physics and chemistry of the galaxy's diffuse matter. Though the ISM may seem emptier than the best laboratory vacuum, its density varies markedly throughout the galaxy. In dense molecular clouds, particularly in the spiral arms, it can reach hundreds or thousands of particles per cubic centimeter, while in more tenuous regions, the density can drop to just a few atoms per cubic meter. Temperatures also vary wildly, from just a few degrees above absolute zero in cold molecular clouds to over 1,000,000 Kelvin in hot ionized regions. This cloudy, dynamic mixture is far from static. The ISM undergoes continuous cycles of transformation. Clouds of gas and dust collapse under gravity to form new stars, which then irradiate their surroundings or explode as supernova, injecting energy and enriching the medium with heavy elements. These processes regulate star formation rates and reshape the galactic environment. One of the ISM's most important components is the molecular clouds, cold and dense regions that act as stellar nurseries. Within these nebulous cocoons, conditions are ripe for the formation of new stars and planetary systems. The thick dust within these clouds absorbs and scatters visible light, often rendering the regions opaque in optical wavelengths, but revealing themselves beautifully in infrared and radio observations. Beyond these dense clouds lie diffuse atomic gas regions and ionized zones, areas where the gas is energized by ultraviolet radiation from nearby young, hot stars. These ionized gas clouds, or H2 regions, glow in characteristic colors and often mark sites of recent or ongoing star formation. Dust grains within the ISM play multiple roles. They absorb ultraviolet and visible radiation, re-emitting it as infrared light, affecting the galactic energy balance. Dust also provides surfaces on which chemical reactions occur, leading to the formation of complex molecules, including organic compounds that serve as precursors to the molecules of life. The ISM also contains cosmic rays, high-energy particles accelerated by supernova shocks and other energetic events that permeate the galaxy, influencing its magnetic field and chemistry. The interplay between cosmic rays, magnetic fields, and the charged gas contributes to the turbulent and magnetized nature of the interstellar medium. Thanks to a broad range of astronomical tools, radio telescopes probing the 21-centimeter hydrogen line, infrared observatories unveiling dust emission, X-ray missions detecting hot gas, and spectroscopy revealing chemical compositions, scientists have developed a rich, multidimensional picture of the ISM's complexity. The interstellar medium is more than empty space. It is the fertile soil from which stars grow and to which they return their ashes. It connects all parts of the galaxy in an intricate web of matter and energy, sustaining the Milky Way's continual cycle of birth, evolution, and renewal. As we journey further through our galaxy, understanding the ISM's properties and processes illuminates the deeper mechanisms driving the cosmos, linking the lives and deaths of stars with the grander evolution of the Milky Way itself. Within the vast and luminous panorama of the Milky Way's billions of stars, countless planets orbit quietly. Worlds that range from scorching infernos to icy realms, from rocky landscapes like our Earth to colossal gas giants dwarfing even Jupiter. These exoplanets, as astronomers call them, each offer a thread in the rich cosmic tapestry that may hold answers to some of humanity's most profound questions. How common are planets? What kinds of worlds exist beyond our solar system? And crucially, might any of them harbor life? The discovery of exoplanets is a relatively recent chapter in astronomy's history. Though speculative fiction and ancient philosophy long pondered the existence of other worlds, it was not until the early 1990s that the first definitive detections of planets orbiting distant stars were made. Since then, technological leaps, especially space-based missions like NASA's Kepler Space Telescope and TESS, Transiting Exoplanet Survey satellite, have revolutionized our understanding, cataloging thousands of exoplanets across the Milky Way and revealing a stunning diversity of planetary systems. Planets form naturally as a byproduct of star formation. As a star condenses from a cloud of gas and dust, a rotating disk of material, the protoplanetary disk, forms around it. Within this swirling circumstellar disk, particles of dust collide and stick together, gradually building up larger bodies over millions of years. Some become rocky planets. Others grow massive enough to attract thick, gaseous envelopes, becoming gas giants. The composition, size, and position of these planets are shaped by the disk's properties and the intricate dynamics of gravitational interactions. Our Milky Way, with its rich concentration of stars in dynamic environments such as spiral arms and star clusters, provides countless laboratories for planet formation. Evidence suggests that planetary systems may be the rule rather than the exception, with estimates indicating that most stars host at least one planet. The array includes super-Earths, larger than our own planet but smaller than Neptune, hot Jupiters orbiting scorchingly close to their stars, and even Earth-sized worlds residing in habitable zones where conditions may support liquid water. Detecting these distant worlds requires ingenuity and exquisite precision. Methods such as the transit technique detect the minuscule dimming of a star's light when a planet passes in front, while radial velocity measurements sense the subtle gravitational wobble a planet induces on its star. More recently, imaging exoplanets directly and analyzing their atmospheric composition through spectroscopy have further deepened our knowledge. The study of exoplanets extends well beyond mere detection. Researchers examine atmospheres for signs of water vapor, oxygen, methane, and other biochemical markers. The search for habitable environments and, potentially, extraterrestrial life hinges on these pioneering efforts. Understanding how planetary systems form and evolve informs us about our own solar system's origins and uniqueness. Statistical surveys have revealed intriguing patterns as well. Stars richer in heavy elements, which form the building blocks of rocky planets, tend to host more planets, highlighting the importance of the galaxy's chemical evolution on planetary demographics. Furthermore, the galactic environment can influence planet formation and stability. For instance, proximity to supernova explosions or densely packed star clusters can affect planetary atmospheres and orbits. As we continue to catalog exoplanets, these discoveries reshape our perspective on the Milky Way, painting it as not just a collection of stars, but as a vast galaxy teeming with diverse worlds. Some could be rocky and temperate like Earth. Others may possess exotic atmospheres and climates unlike anything we've imagined. Imagining the prospects of exploring these distant worlds, even with our current technology, stretches the imagination and pushes the boundaries of science and engineering. Each new exoplanet discovery brings us closer to answering timeless questions about life's prevalence and the nature of our place in the cosmos. Thus, the Milky Way is not only our star-studded home, but potentially a profound cosmic archipelago of planets, waiting to be understood, explored, and perhaps one day, visited. As our journey through this majestic galaxy continues, we will explore the movement of stars and planetary systems along the cosmic highways forged by gravity and time, weaving together the complex dance that sustains this vibrant galactic ecosystem. Delving into the Milky Way, one quickly discovers that it is not a static, unchanging vista, but a dynamic and ever-moving cosmic city where stars journey along intricate paths, weaving through the galaxy's structure in a grand orbital ballet. The movement and orbits of stars, often called the cosmic highways, are governed by the gravitational field of the galaxy, an invisible but powerful force shaped by both visible matter and the elusive dark matter halo enveloping the Milky Way. Understanding these star motions reveals the underlying architecture and dynamic life of our galactic home. At the core of this celestial choreography lies gravity, the dominant force governing the motion of stars, gas, and dark matter alike. Every star orbits the center of the galaxy under gravitational attraction, moving along paths that reflect the galaxy's mass distribution and evolutionary history. Stars in the Milky Way generally follow roughly circular orbits within the galactic disk, especially those in the spiral arms where gas and young stars reside. These orbits are not fixed lanes, like cars on a road, but more akin to shifting patterns in a flowing river, with stars moving forward while gently oscillating up and down relative to the galactic plane. This oscillation is due to the gravitational pull of the mass concentrated in the disk, peaking near the midplane and diminishing away from it. The Sun itself completes an orbit around the galactic center approximately every 225 to 250 million years, traveling at a speed near 828,000 kilometers per hour. Beyond the relatively ordered disk, stars in the galactic bulge and stellar halo follow different orbital patterns. In the bulge, stellar orbits are more elliptical and randomly oriented, reflecting a dense and dynamically active region molded by past mergers and complex gravitational interactions. Halo stars exhibit even more eccentric orbits, often plunging through the disk at steep inclinations, the remnants of dwarf galaxies consumed or stirred by the Milky Way's gravity over billions of years. The full complexity of stellar motion is unveiled through kinematic studies, analyzing velocities and proper motions, angular shifts over time, of stars. Astronomers employ spectroscopy to measure Doppler shifts in stellar spectra, revealing radial velocities, movement toward or away from us, and leveraging precise astrometric data, especially from missions like ESA's Gaia, to map tangential velocities. Combining these reveals three-dimensional motions, enabling the reconstruction of stellar orbits and revealing the galaxy's gravitational potential. These motions weave together into large-scale patterns. The rotation curve of the galaxy, for example, charts how orbital velocity depends on distance from the center. Intriguingly, observations show that stars in the outer parts of the Milky Way orbit faster than expected, based on visible matter alone, a key piece of evidence for the presence of dark matter halo, providing additional mass and gravitational pull. Within the spiral arms, stars and gas do not move purely with the arms, but rather pass through spiral density waves, regions of enhanced gravitational density that compress gas clouds, triggering star formation. This causes stars to bunch and disperse in patterns over millions of years, much like cars slowing at a traffic jam and then accelerating onward. This model explains why spiral arms persist as recognizable features without being rigidly fixed structures. Stars also form moving groups or stellar streams, coherent populations with common origins which trace the Milky Way's accretion history. Some streams orbit within the halo, remnants of dwarf galaxies shredded by tidal forces and absorbed into the Milky Way. These streams offer crucial clues to the galaxy's formation and growth through cosmic time. In the Sun's neighborhood, stellar velocities show the influence of the galactic bar and spiral arms, contributing to subtle but measurable departures from simple circular motion. These perturbations hint at the complex gravitational interplay shaping our local cosmic environment. Mapping and modeling these stellar orbits is more than an academic exercise. It illuminates the Milky Way's mass distribution, the role of dark matter, the history of galactic mergers, and the dynamic environment that shapes planetary system stability. This knowledge connects to broader questions in astronomy and cosmology about how galaxies form and evolve. As we continue our exploration, the cosmic highways guide us toward less visible but no less critical components, such as the invisible dark matter scaffolding and the pervasive galactic magnetic fields, forces that mold the Milky Way's ongoing story of structure, motion, and life. The movement of stars within the Milky Way is a magnificent dance, a testament to the galaxy's complexity, beauty, and the intricate gravitational forces that govern it. This flowing stellar movement is the lifeblood of the galaxy, connecting its regions and sustaining the dynamic equilibrium between destruction and creation. A cosmic symphony, inviting us ever deeper into the heart of our galactic home. Hidden beneath the luminous tapestry of stars in the Milky Way lies a profound and mysterious substance that neither emits nor absorbs light: dark matter. This elusive material forms the invisible backbone of our galaxy, shaping its structure, dynamics, and evolution in ways we are only beginning to understand. Though imperceptible through direct observation, the evidence for dark matter's presence is overwhelming and fundamental to modern astrophysics. The story of dark matter begins in the 1930s, when astronomers first noticed an anomaly in the motions of galaxies and their constituent stars. Vera Rubin's pioneering studies in the 1970s of galactic rotation curves, the way orbital velocities of stars change with distance from the galactic center, revealed that stars far from the Milky Way's core orbit much faster than expected, based on the observed distribution of visible matter alone. According to Newtonian gravity, outer stars should slow down dramatically, much like planets in our solar system orbit more slowly at greater distances from the Sun. Instead, stars maintain high speeds even at vast distances, implying the presence of a tremendous unseen mass exerting gravitational pull. This invisible mass is what we call dark matter. Unlike ordinary matter, which interacts through electromagnetic forces and can be detected by the light it emits or absorbs, dark matter does not interact with electromagnetic radiation, making it practically invisible. Its nature remains one of the greatest enigmas in physics. Various candidate particles have been proposed, from weakly interacting massive particles, WIMPs, to axions and sterile neutrinos, but none have yet been directly detected despite extensive experimental efforts. Within the Milky Way, dark matter forms a vast, roughly spherical halo that extends well beyond the visible stellar disk, encompassing the entire galaxy and influencing the motions of stars and gas across all scales. Estimates suggest that about 85% of the Milky Way's total mass is in the form of dark matter, vastly outweighing the combined mass of stars, gas, and dust. This dark matter halo is crucial for the galaxy's stability. Without it, the outer regions would not maintain their rapid rotation, and the galaxy might simply fly apart. The gravitational influence of dark matter extends even further. It governs the behavior of satellite galaxies orbiting the Milky Way and plays a defining role in galaxy formation and clustering on larger cosmic scales. Dark matter's presence acts as scaffolding around which ordinary matter clusters, guiding the formation of galaxies and large-scale structures in the universe. The shape and extent of the Milky Way's dark matter halo continue to be actively studied using observations of stellar motions, gravitational lensing, and numerical simulations. These studies help refine our models of galactic formation, merger history, and evolution. Though invisible directly, dark matter also interacts gravitationally with ordinary matter, affecting the orbits of stars, the distribution of gas, and the propagation of light along curved spacetime. It subtly influences the paths of cosmic rays and the behavior of magnetic fields in the galaxy, intertwining with other dynamic processes within the Milky Way. In the ongoing quest to understand dark matter, astronomers and physicists employ a broad range of observational and experimental techniques, from mapping stellar streams that trace the gravitational potential to deep underground detectors searching for elusive dark matter particles. Future missions and observatories promise to shed new light on this cosmic mystery. Dark matter is not just an abstract concept, but the silent architect of the Milky Way's structure and fate, shaping the galaxy in ways both grand and subtle. As our exploration continues, uncovering its secrets will deepen our understanding of the cosmic web, linking galaxies across the universe, and illuminate the fundamental nature of matter and gravity itself. Permeating the vast reaches of the Milky Way, invisible yet immensely influential, are magnetic fields, cosmic threads of magnetism that weave through interstellar gas and dust, shaping and shielding the galaxy in subtle yet profound ways. These galactic magnetic fields are an essential component of the Milky Way's environment, guiding the motion of charged particles, influencing star formation, and protecting planetary systems like our own from cosmic radiation. Though invisible to our eyes, magnetic fields reveal their presence through their effects on matter and light. One way astronomers detect these fields is by observing the polarization of starlight and radio waves. When light passes through regions threaded with magnetized dust grains, it becomes polarized, meaning its electric fields align along certain directions, revealing the orientation of the magnetic field lines. Similarly, charged particles spiraling around magnetic fields produce synchrotron emission, a telltale glow in radio frequencies that maps the galactic magnetism. Within the Milky Way, Magnetic fields are intricately linked with the structure of the interstellar medium. They thread through the molecular clouds where stars form, helping to regulate the collapse of gas by providing pressure against gravity and affecting the turbulence within these clouds. This magnetic support can determine when and where new stars will ignite, making magnetism a key player in the galaxy's stellar birth cycles. Besides their role in star formation, galactic magnetic fields guide cosmic rays, highly energetic charged particles originating from supernova explosions and other energetic sources. The magnetic fields trap and deflect these particles, affecting their trajectories and slowing their escape from the galaxy. This containment helps moderate the cosmic radiation environment experienced within the Milky Way, particularly shaping conditions around planetary systems and potentially influencing biological evolution. The geometry of the Milky Way's magnetic field is complex. Studies suggest a large-scale spiral pattern aligned roughly with the galactic spiral arms, combined with local fluctuations caused by supernova remnants, turbulent gas motions, and stellar winds. These smaller-scale variations create a dynamic and evolving magnetic landscape. Moreover, the fields extend into the galactic halo, influencing the flow of gas between the disk and halo, and possibly playing a role in phenomena such as galactic fountains, where heated gas cycles between the disk and halo, and the accretion of matter from the intergalactic medium. The origin of these magnetic fields likely lies in the amplification of weak seed fields by a dynamo effect, a process driven by the galaxy's rotation and turbulent motions within the interstellar medium. This cosmic dynamo sustains and organizes the magnetic fields over billions of years, adapting as the galaxy evolves. Understanding galactic magnetism requires a multi-wavelength observational approach, harnessing radio, infrared, and even X-ray data, alongside sophisticated simulations that capture the interplay between magnetic fields, gas dynamics, and cosmic rays. These studies reveal that magnetism is not a mere backdrop, but an active participant in shaping the Milky Way's structure and life cycle. For Earth and our solar system, the Milky Way's magnetic environment provides a protective shield, reducing exposure to harmful cosmic rays that could otherwise impact atmospheres and biology. Complemented by our Sun's own complex magnetic field and heliosphere. This layered magnetic cocoon factors into the delicate balance sustaining life on our planet. In the grand cosmic ballet, galactic magnetism is an unseen actor, an ethereal force stitching together stars, gas, and cosmic rays, guiding flows of matter and energy, and preserving the conditions necessary for the ongoing evolution of the Milky Way. As our astronomical tools grow ever more sensitive, we continue to unravel the threads of this magnetic web, deepening our appreciation for the invisible forces that govern the cosmos. The Milky Way, serene and grand as it appears in our night sky, is the product of billions of years of cosmic evolution, a dynamic entity shaped by myriad processes, interactions, and transformations since its infancy shortly after the Big Bang. Understanding how our galaxy grew over time offers us profound insights not only into its structure and composition, but also into the broader mechanisms of galaxy formation and evolution that sculpt the universe. In the earliest epochs, roughly 13.6 billion years ago, the universe was a hot, dense sea of primordial hydrogen and helium, with tiny fluctuations in density marking the seeds of future structures. Under the relentless pull of gravity, these fluctuations began to coalesce, forming the first clumps of dark matter and gas, known as proto-galactic fragments. Within these early building blocks, the very first stars ignited, and chemically simple clouds gradually enriched through stellar nucleosynthesis. The Milky Way's formation likely began as such a cloud, growing over hundreds of millions of years through the gradual accretion and merging of smaller gas clouds and dwarf galaxies, a process echoed by the hierarchical model of galaxy formation. These smaller progenitor galaxies were cannibalized and assimilated into what eventually became the Milky Way's bulge, halo, and disk. Evidence of this growth by merging is etched in the stellar streams that traverse the galactic halo, faint, elongated bands of stars that are remnants of dwarf galaxies shredded by tidal forces. By analyzing these streams and the chemical signatures of their stars, astronomers reconstruct past merger events, discovering that the Milky Way's history is one of continual assembly. Over time, the galactic disk formed through the settling of gas into a rotating, flattened structure where ongoing star formation built successive generations of stars. The disk's spiral arms emerged, shaped by density waves and dynamical interactions, becoming the bustling nurseries for young stars. The formation of the central galactic bar added complexity and dynamism to the galaxy's inner regions, directing gas flows inward and nurturing central star formation. Throughout its evolution, feedback from star formation, stellar winds, radiation pressure, and supernova explosions regulated the Milky Way's growth by heating and stirring the interstellar medium, influencing the efficiency and distribution of new stars. These processes balanced the inflow of cold gas from the galaxy's surroundings and the consumption of gas into stars, sustaining the Milky Way's star formation over billions of years. On the outskirts, the galaxy's extended dark matter halo grew as it absorbed faint, diffuse matter and satellite galaxies, reinforcing the gravitational well that shapes the motions of visible mass. This dark halo plays a central role in stabilizing the Milky Way's structure and enabling the retention of gas necessary for continued star formation. Recent observations and simulations illustrate that the Milky Way continues to evolve. Interactions with nearby galaxies, the large and small Magellanic Clouds, along with myriad dwarf satellites, induce tidal forces and streams which will eventually culminate in larger mergers. The most dramatic of these awaited events is the anticipated collision with the Andromeda Galaxy in several billion years, which will profoundly reshape both giants. Throughout its lifetime, the Milky Way transformed from a small, chaotic proto-galaxy into a majestic, structured barred spiral. Its evolution is marked by cycles of accretion, star formation, and feedback, interwoven with the dark matter framework and cosmic environment. By studying stellar populations, gas dynamics, and the motions of stars, scientists piece together this vast saga, uncovering how the Milky Way grew from primordial ingredients into the galaxy we call home. As we proceed in exploring our cosmic neighborhood, understanding the Milky Way's evolution informs not just our galactic heritage, but also the universal story of cosmic structure formation, a grand narrative stretching from the dawn of time to the ever-unfolding future of the universe. As we journey through the Milky Way, it becomes clear that our galaxy's story is not one of serene isolation, but of dynamic interaction and cosmic transformation. A tale dominated by the phenomenon astronomers evocatively term galactic cannibalism. Over billions of years, the Milky Way has grown, in part, by absorbing smaller galaxies, tearing them apart, and assimilating their stars and gas into its vast structure. These events leave behind striking footprints in the form of stellar streams, elongated, coherent trails of stars that arc gracefully through the galaxy's halo and provide rich clues to its violent past. Imagine a dwarf galaxy venturing too close to the Milky Way's immense gravitational pull. Tides, the differential gravitational forces across the dwarf, stretch and deform it, gradually stripping stars and gas from its outskirts. Over cosmic timescales, these torn fragments trail behind the dwarf, creating stellar streams that trace the orbit of the original galaxy. Eventually, the dwarf's core may be fully disrupted or absorbed, its material dispersed and mixed into the Milky Way's halo and disk. One of the most prominent examples is the Sagittarius dwarf spheroidal galaxy, discovered in the 1990s. This small galaxy is in the final throes of disintegration, wrapping long, slender streams of stars around the Milky Way in a complex, looping pattern. Its streams stretch over tens of thousands of light-years, providing astronomers with a living laboratory to study the mechanics of tidal disruption and galactic assembly. These stellar streams are detected through a combination of precise star position measurements, velocities, and chemical compositions. Stars within a stream share common properties that distinguish them from the general stellar population, indicating shared origins. Advanced surveys and telescopes, such as the Gaia mission, have greatly expanded our ability to find and analyze these streams, unveiling a rich and intricate network that maps past merger events. Galactic cannibalism is a fundamental mechanism driving the hierarchical growth of galaxies. Smaller galaxies, themselves formed from even tinier progenitors, merge and amalgamate over time, leading to increasingly massive and complex systems. This process is thought to have shaped much of the Milky Way's halo and influenced the thick disk and even parts of the bulge. Mergers deposit not only stars, but also gas, which can fuel new waves of star formation or feed central black holes, altering the galaxy's morphology and dynamical state. The scars of these events can persist for billions of years as streams, shells, or ripples in the stellar distributions. Beyond their role as historical records, stellar streams and mergers help constrain the distribution of dark matter within the Milky Way. The gravitational effects shaping the orbits of tidal debris reveal the contours of the invisible dark halo, informing models of galactic mass and structure. Occasionally, minor mergers may perturb the Milky Way's disk, triggering patterns such as spiral arms or warps in the galactic plane. Such events bring dynamism and complexity to the galaxy's evolution, emphasizing that it is far from static. Looking ahead, the Milky Way's future is forecast as a grand merger with the nearby Andromeda Galaxy, an event that will reshape both galaxies dramatically. This anticipated collision, occurring billions of years from now, will be a cosmic climax echoing the processes witnessed through the countless smaller mergers of the past. Thus, stellar streams and galactic cannibalism are more than mere curiosities. They are the living narrative threads of the Milky Way's growth and transformation. They remind us that our galaxy is a dynamic ecosystem shaped by continual interaction, rejuvenation, and cosmic assimilation, a majestic giant born of countless smaller galaxies, endlessly evolving in the vastness of space. As we venture from the bright, bustling disk of the Milky Way into the more remote outskirts, we find ourselves at the galaxy's edge, a vast and enigmatic region known as the galactic halo. This halo stretches hundreds of thousands of light-years beyond the stellar disk, representing a diffuse, spherical envelope containing not only ancient stars and globular clusters, but also an invisible reservoir of dark matter that defines the galaxy's true boundary. The halo's stars are ancient relics, among the oldest known in the Milky Way, often with low metallicity, meaning they contain fewer elements heavier than hydrogen and helium, a clue to their primordial origins. These stars wander on highly elliptical and inclined orbits, unlike the relatively circular paths in the galactic disk. Often sparsely distributed, they quietly testify to the galaxy's early formation epochs and to the dynamic mergers that shaped its evolution. Nestled within the halo are the globular clusters, dense, spherical collections of hundreds of thousands, sometimes millions, of stars that orbit the galactic center as coherent units. These clusters provide invaluable insight into the conditions of the early universe and the processes that formed the first generations of stars. Their ancient ages, combined with detailed stellar population analyses, enable astronomers to probe the chronology of the Milky Way's assembly. Beyond the stars lurks the more mysterious component, the circumgalactic medium, CGM, an extended halo of hot, ionized gas glowing in X-rays and stretching even further than the stellar halo. This tenuous gas acts as a colossal reservoir, feeding material back into the galactic disk to fuel ongoing star formation, while also regulating the outflow of gas driven by stellar winds and supernovae. The CGM plays a crucial ecological role, linking the galaxy to the intergalactic medium and the broader cosmic web. Satellite galaxies, small companion galaxies gravitationally bound to the Milky Way, also reside in this region. Some, like the Large and Small Magellanic Clouds, are visible to the naked eye from the southern hemisphere and provide laboratories for studying galaxy interaction, accretion, and tidal disruption processes. Others are newly discovered ultra-faint dwarfs, barely detectable yet vitally important for understanding dark matter distribution and galactic formation history. Stretching beyond the halo, the Milky Way merges seamlessly into the intergalactic void, where the tenuous filaments of the cosmic web link galaxies in an intricate network of matter and energy. This boundary is not sharp but fluid, marking an ongoing exchange of gas, dark matter, and even galaxies themselves within the local group and larger cosmological structures. Our understanding of the galaxy's edge has been revolutionized by powerful instruments spanning the electromagnetic spectrum, from optical surveys mapping faint halo stars to X-ray telescopes unveiling the hot CGM. These observations combine with theoretical simulations to reveal a dynamic, evolving periphery that both shields and nourishes the galaxy's inner regions. In embracing the Milky Way's edge, we glimpse the interconnectedness of cosmic scales, from individual stars to the grand architecture of the universe, reminding us that our galactic home is both a solitary island of light and a nexus in the vast cosmic sea, quietly sailing through the boundless expanse. Surrounding our majestic Milky Way like a celestial family are its satellite galaxies, small companion galaxies gravitationally bound and orbiting our galactic home. These neighbors, often faint and irregularly shaped, provide invaluable clues to the history, evolution, and environment of the Milky Way. They embody a dynamic cosmic community, illustrating the processes of galactic interaction, growth, and transformation that have shaped our corner of the universe. The most prominent satellites of the Milky Way are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as hazy patches in the night sky. These irregular dwarf galaxies are relatively massive compared to other satellites, containing billions of stars, nebulae, and regions of active star formation. The Magellanic Clouds orbit near the Milky Way's periphery and interact gravitationally with both the Milky Way and each other, producing complex tidal features such as the Magellanic Stream, a gaseous tail stretching over 100 degrees across the sky. In addition to these prominent companions, astronomers have identified dozens of fainter dwarf satellite galaxies in recent decades, many discovered through wide-field sky surveys using sensitive instruments capable of detecting their faint stellar populations. These ultra-faint dwarf galaxies are among the smallest and least luminous galaxies known, often consisting of just a few thousand stars packed into a relatively small volume. These satellite galaxies are particularly important for understanding dark matter and galaxy formation. Due to their low mass and shallow gravitational wells, they are sensitive to external forces such as tidal stripping and ram pressure stripping as they orbit the Milky Way, processes which can remove gas and distort their shapes. Their star formation histories also shed light on the effects of environment and feedback in low-mass systems. Many of these satellites inhabit the Milky Way's dark matter halo, embedded within its vast gravitational influence. Their orbits can be complex, some on polar orbits sweeping above and below the galactic plane, while others orbit closer to the disk. Tracking their trajectories reveals insights into the Milky Way's gravitational potential and its assembly history. Some satellites may be remnants of groups that were accreted together. The interaction between the Milky Way and its satellites is a cosmic dance with lasting consequences. Tidal forces exerted by the Milky Way can pull stars and gas from satellites, creating stellar streams and tidal tails that gradually blend into the halo's structure, evidence of ongoing galactic cannibalism. Conversely, these interactions can trigger star formation in satellites or even disturb the Milky Way's own disk, contributing to spiral arm dynamics and warp features. Beyond their role as dynamic actors, satellite galaxies are time capsules preserving the conditions of the early universe. Many contain extremely old, metal-poor stars that offer a window into the primordial epochs of galaxy formation and the earliest chemical enrichment. Our technological advancement has fueled a renaissance in discovering and studying these satellites, from space telescopes like Gaia mapping their stellar content and motions with exquisite precision, to large ground-based surveys uncovering faint and distant examples. Future telescopes promise deepening our understanding of this galactic retinue. Thus, the Milky Way's satellite galaxies are more than mere companions. They are vital keys to decoding the complex interplay of gravity, dark matter, and baryonic processes that sculpt galaxies. They enrich our understanding of how the Milky Way formed, grows, and continues to evolve within the cosmic web, standing as whispered echoes of the universe's grand, ongoing narrative. Our Milky Way is but one island in a vast cosmic ocean teeming with countless galaxies, many of which gravitate together in cosmic communities known as galaxy groups. Among these is the local group, the galactic neighborhood to which the Milky Way belongs. This assembly of galaxies provides crucial context for understanding the environment, history, and future of our home galaxy. The local group is a gravitationally bound collection of over 50 galaxies, ranging from majestic spirals like our Milky Way and its close neighbor, the Andromeda Galaxy, to numerous smaller dwarf galaxies. Spanning roughly 10 million light-years across, this galactic neighborhood sits comfortably within the larger cosmic web, influencing and being influenced by the surrounding universe. The two giants, the Milky Way and Andromeda, dominate the local group's mass and gravitational pull. Each contains hundreds of billions of stars and retinues of satellite galaxies. They orbit a common center of mass and are slowly converging, a dynamic dance that will culminate in a colossal collision and merger billions of years from now. The third largest member, the Triangulum Galaxy, M33, is a smaller spiral galaxy that also interacts gravitationally within the group, contributing further complexity to the group's dynamics. Alongside these major players are dozens of dwarf galaxies, many of which orbit the Milky Way or Andromeda, while others drift in the intergalactic spaces between. The local group exhibits a range of galactic types: elliptical, irregular, and dwarf spheroidal galaxies, each offering insight into differing evolutionary paths conditioned by their environments. These smaller systems are often vulnerable to tidal stripping and other transformative effects from their more massive neighbors, a testament to the hierarchical nature of galaxy formation. Studies of galaxy distributions, motions, and interactions within the local group inform models of dark matter distribution, galaxy formation, and the gravitational scaffolding of the universe. For example, mapping the orbits and velocities of satellite galaxies helps astronomers infer the shape and extent of the Milky Way's and Andromeda's dark matter halos. Beyond their scientific significance, the galaxies of the local group create a compelling cosmic tapestry, a menagerie of stellar cities, each with its own history and physical character. Together, they form a microcosm reflecting the large-scale structure of clusters and superclusters that define the universe on grand scales. Understanding our place within the local group thus expands our cosmic address, linking the Milky Way's story to that of its neighbors and setting the stage for future exploration. As we later consider the collision course with Andromeda and beyond, the local group stands as a reminder of the dynamic and interconnected nature of galaxies, bound by gravity and woven into the evolving fabric of the cosmos. Amid the cosmic expanse where the Milky Way reigns as a majestic spiral galaxy, a slow, inexorable dance of gravity weaves a dramatic and transformative future. A galactic encounter destined to reshape our cosmic neighborhood over the next several billion years. This unfolding saga centers on the Andromeda Galaxy, our colossal spiral neighbor, currently hurtling toward us on a collision course that promises not destruction, but monumental rebirth. The Andromeda Galaxy, also known as M31, is the largest galaxy in our local group and lies roughly 2.5 million light-years away. Though seemingly distant, it is approaching the Milky Way at a velocity of about 110 kilometers per second, closing the gap between the two massive spirals. This motion has been meticulously measured through advanced observations of stellar motions and cosmological modeling, revealing a future event of profound significance. In approximately 4 billion years, Andromeda and the Milky Way will collide. This galactic collision is not a head-on smash in the classical sense, but rather a complex gravitational interaction unfolding over billions of years. As their immense gravitational fields intertwine, the two galaxies will begin to distort each other's disks, pulling out long tidal tails of stars and gas, triggering bursts of star formation as gas clouds compress in turbulent shocks. Despite the enormous number of stars involved, hundreds of billions in each galaxy, the vast distances between individual stars mean that direct stellar collisions will be exceedingly rare. Over the course of this extended cosmic encounter, repeated passes and gravitational tugs will gradually consume the two spirals, ultimately merging them into a single, more massive elliptical galaxy. This new galactic entity, sometimes colloquially called Milkomeda, or the Milky Andromeda, will be vastly larger, with a reshaped structure reflecting the complex interplay of dynamics, star formation, and central black hole activity during the merger. This transformative process will influence the fates of star systems within both galaxies. Our solar system, currently in a stable orbit around the Milky Way's galactic center, may be displaced, propelled into a new orbit, or even ejected into the galactic halo, though this trajectory is difficult to predict precisely. The environment around Earth may undergo changes in radiation exposure or encounter new interstellar conditions, but life itself is expected to continue for billions of years beyond this event. Beyond the local implications, this merger exemplifies a fundamental mechanism of galactic growth across the universe. Throughout cosmic history, galaxies have frequently merged and interacted, building larger and more complex systems. The Milky Way-Andromeda collision is a front-row seat to this grand cosmic evolution, one we are privileged to observe and predict. Observational evidence of galactic collisions elsewhere, spectacular interacting galaxies with swirling tails and bursts of star formation, provide a vivid glimpse into the likely future evolution of our home. Numerical simulations further allow astrophysicists to visualize the stages and outcomes of the merger, informing our understanding of galactic dynamics, star formation, and black hole growth. In parallel, this collision foretells a more distant destiny for our cosmic neighborhood. The local group's eventual future includes further mergers and interactions with neighboring galaxy groups, gradually reshaping the large-scale structure of the universe. Meanwhile, the accelerating expansion of space driven by dark energy will progressively isolate our once vibrant cosmic context. The approaching convergence of the Milky Way and Andromeda thus invites us to fathom not only the physical transformations, long timescales of orbital dynamics, star births and deaths, morphological metamorphosis, but also the philosophical and poetic implications. It reminds us of the deep interconnectedness and impermanence of cosmic structures, the unending cycles of creation and transformation playing out on unimaginable scales. As our journey through the Milky Way's majesty continues, this anticipated cosmic embrace with Andromeda stands as a grand finale and a beginning, an awe-inspiring testament to the dynamic and evolving universe of which we are an intrinsic part. Embarking on a voyage across the vast expanse of the Milky Way is an invitation to imagine a journey on a scale so immense that it challenges our very concepts of distance, time, and technology. The Milky Way, spanning roughly 100,000 to 120,000 light-years in diameter, is home to hundreds of billions of stars, nebulae, and complex structures, an entire cosmic city that beckons explorers to traverse its luminous streets one day. But what would it really take to journey across our galaxy? Could such a voyage ever be possible? To begin, it is essential to grasp the colossal scale involved. A single light-year, the distance light travels in 1 year, is about 9.46 trillion kilometers, nearly 6 trillion miles. Traveling at the speed of light, a beam from our Sun's relatively close neighbor, Alpha Centauri, still takes over 4 years to arrive. The furthest reaches of the Milky Way are tens of thousands of light-years away. Even if we sent a spacecraft traveling at an unprecedented speed, far beyond present-day capabilities, it would take tens of thousands of years to cross the galaxy. The concept of propulsion comes into sharp focus here. Current human spacecraft, such as the Voyager probes, travel at a fraction of the speed needed to make interstellar trips in reasonable timescales, around tens of kilometers per second. To voyage across the Milky Way within a human lifetime would require propulsion systems capable of reaching significant fractions of light speed. Concepts under study include nuclear pulse propulsion, antimatter drives, and the speculative but tantalizing idea of light sails propelled by powerful lasers. Traveling at, say, 10% of the speed of light would drastically reduce the journey time to hundreds of thousands of years, still beyond human lifespans, but more manageable in cosmic terms. However, sustaining such speeds presents immense technological hurdles. Fueling, navigation, shielding against cosmic radiation and interstellar dust, and the psychological and biological needs of travelers all pose monumental challenges. The vast emptiness between stars means that, despite the dangers that high-speed travel through interstellar dust could pose, the risk of collision with solid objects is relatively low, but still non-negligible. Protective shielding or advanced monitoring and maneuvering systems would be essential. An alternative approach to exploring the Milky Way might involve robotic probes equipped with artificial intelligence, capable of autonomous decision-making and adaptation, transmitting data back to Earth over vast distances. Projects like Breakthrough Starshot imagine launching swarms of tiny probes propelled by powerful ground-based lasers to nearby stars, like Alpha Centauri, within decades, potentially revolutionizing our ability to explore beyond our solar system. Beyond propulsion lie navigation challenges. Mapping a course through a densely packed galaxy with its complex gravitational fields, dynamic stellar motions, and dark matter influences requires precise stellar cartography and advanced computational capabilities. Spacecraft would need to constantly update their positions relative to multiple reference points and adapt to shifts in the Milky Way's structure over time. Life support and sustainable ecosystems pose additional hurdles for manned voyages. The psychological isolation, radiation exposure, and resource regeneration during multi-generational voyages demand revolutionary advances in closed ecological systems and human biology. Imagining journeys across the Milky Way invites us to consider time dilation effects predicted by Einstein's theory of relativity. As spacecraft approach the speed of light, time aboard them would slow relative to observers on Earth, allowing travelers to experience shorter durations for the voyage. While theoretically promising, achieving such speeds remains firmly in the realm of advanced physics and future technology. In the meantime, our most practical means of traveling across the Milky Way is through observation, sending telescopes and probes to study distant objects, using light and other signals to build maps of our galactic environment, deepening our understanding and fueling our imagination. Ultimately, envisioning a voyage across our galaxy challenges our ingenuity, perseverance, and mirrors humanity's timeless spirit of exploration. While physical journeys may lie far in the future, the knowledge we gather today lights our path toward that dream, kindling hope that someday dreams of traversing the Milky Way will become realities. Journeys not just across space, but across the boundless frontiers of human curiosity and cosmic understanding. As our journey through the Milky Way draws to a contemplative close, we stand in quiet awe of the galaxy that cradles our existence, an immense, dynamic, and intricate cosmic home that has shaped not only the stars and matter within it, but also our very understanding of ourselves and the universe. The Milky Way is more than a celestial spectacle. It is a profound reminder of our place in the cosmos, a beacon of connection, mystery, and inspiration. Reflecting on the vastness of the Milky Way, we begin to appreciate the fragility and uniqueness of the Earth amid billions of stars and worlds. Our planet's rich diversity of life owes its origins to cosmic processes that unfolded over billions of years. Stellar births, supernova explosions spreading heavy elements, the coalescence of planets from interstellar gas and dust. Every atom within us tells a story linked to the ancient cycles of the galaxy. The Milky Way embodies the dynamic interplay of creation and destruction, of order and chaos. Its spiral arms nurture the birth of new stars, while its halo echoes with ancient relics and ghostly stellar streams, reminders of a turbulent past shaped by mergers and cosmic cannibalism. The invisible framework of dark matter and the subtle threads of galactic magnetism weave an unseen architecture supporting this grand celestial symphony. For humanity, understanding the Milky Way expands the scope of our knowledge and fuels the spark of curiosity that defines our species. From early stargazers who named the Milky Band across the night sky to today's astronomers peering deep with sophisticated instruments, the galaxy has been a source of wonder, navigation, and philosophical reflection. It challenges us to confront questions of origin, destiny, and our intimate connection to something greater than ourselves. As we map its structures and uncover the lives of its stars, we not only learn about the physical universe, but also engage with the timeless human endeavor to find meaning and context. The Milky Way is both our cosmic address and our bridge to the universe's vast unknowns, a reminder of the delicate balance of forces allowing life and complexity to flourish. Looking to the future, the Milky Way continues to evolve, and so does our relationship with it. Advancements in technology and space exploration promise deeper insights, from understanding exoplanets that may host life to unraveling the nature of dark matter. The prospect of interstellar voyages, while distant, urges us to dream beyond our planetary confines and embrace a shared destiny among the stars. Ultimately, the Milky Way is a testament to the unity of matter, energy, and time, a grand, swirling journey through which everything is connected. It invites us to cherish our place within this cosmic ocean, to seek knowledge with humility and wonder, and to recognize that, as inhabitants of this galaxy, we are explorers not just of space, but of existence itself. In this reflection, the Milky Way's meaning transcends astronomy. It becomes a canvas upon which humanity's story is painted, a symbol of our aspirations, our mysteries, and our enduring quest to understand the profound depths of the universe and our role within its boundless expanse.